Good morning. My name is Nitish Jhawar and I am currently studying at IIT Bombay Computer Science Department, second year. I cleared my joint entrance exam in the year 2009 and secured an All India rank of 7. Today we are here to discuss the topic indefinite integral. So as I assume that you all know differentiation, so for the purpose of this chapter, we will interpret integration basically as a reverse or inverse process of differentiation. There are various other interpretations of integration as well, as you will see in the later chapters like definite and area. But for this chapter, we will contain ourselves to just interpreting it as reverse of differentiation. Okay, so let me write down the formal definition so that we can proceed forward. Okay, so suppose you have a function fx that is differentiable. Okay, so let's take this pen. Fx is differentiable, that is d by dx of fx is say fx. Okay, so by the reverse process, what I am trying to say here is that if I say that the derivative of small fx is capital Fx, then rearranging this, we have fx is equal to fx dx. This is the symbol for integral, summation sign, this holds. This implies this. Fx derivative is say capital Fx, then fx is integral of fx dx. And since we are studying indefinite, so as you will see, we are not putting any limits. So we will explain it later step by step. So right now I am trying to say is it's the inverse process of differentiation. Okay, so this is the function that is being integrated is called the integrand. Okay, that is fx here is called integrand, just for the formal term if you want to know. And fx here is what is called antiderivative, or in other words primitive function. Okay, so someone may use these terms, so it's better to know all the proper terminology involved. So this is as far as the definition goes, as you need to know for the scope of this chapter. Okay, so this is the definition. So the next term that I'm going to tell you about is the constant of integration. Okay, it's a very important term, integration. So as you have seen here that integration is the inverse process of differentiation. So what I'm going to do here is say, you know that d by dx of small fx is capital Fx. Okay, so this implies that since we know that derivative of a constant function, d by dx of a constant function, constant is 0. From differentiation you know that. So using these two, I can say that if I write this, that is fx plus some constant, this should also give me fx, because by the some rule of differentiation I can see that derivative of this thing in the brackets can be written as derivative of the first thing plus derivative of the second, and the second is 0 derivative, so this is this. So now implying the inverse of differentiation as integration, we see that fx plus constant is integral fx dx. So the purpose of this entire little proof was that whenever you integrate, there will be a constant. You can't just say, okay, integral of this function is this function. It is this function plus a constant whose value will be determined if some other relation is given, which is generally not the case here. We are not interested in finding the constant, but we should know that there is a constant. Sometimes you may forget to write it and it may lead to some problem. So remember, this is constant of integration. So till now you know the definition for integration, and that there is a term known as constant of integration, and why is it there. Okay, so using this, now first of all I'm going to write some properties on integration, and then we'll see some of the methods of integration. And note one thing, that the constant that I'm talking about is obviously real here, so just for you to know. Okay, so now we have reached properties of integration. Okay, so the first property is that integral a fx dx can be written as a integral fx dx, obviously where a epsilon constant and is independent of x constant. Okay, so I can give you the rough idea of this proof. Let me do one of these. There are 3-4 properties, then you will get the idea. So say a fx d by not like this, sorry. Since we know integral of dx is say some function, say let's say tx, then we would know that a fx would have been tx d by dx, because if this would have happened, then only we would have implied this. So since we know a is a constant, what we can do is fx can be taken as d by dx 1 by a tx. Okay, this is one and the same thing. And then now integrating both sides or using the inverse, we know that fx dx integral times a is again what? Nothing but tx. So just a little manipulation using that. In differentiation the derivative comes out and it is the inverse process. So I have written down the proof of how a fx dx can be written as a times integral fx dx. So this is the basic method that we use to prove such little theorems. Like again the second theorem, that is integral fx plus gx dx can be written as fx dx plus integral gx dx. Okay, so let's again do the proof. So we say that say fx is derivative of d by dx of capital Fx. Okay, and gx is d by dx of capital Gx. Now adding this, I'll get fx plus gx, and by properties of differentiation I know that this thing can be written as combined this. Okay, till now it is clear. So now taking integration on both sides, I have fx plus gx dx integral is nothing but fx plus gx. But what was fx? But fx was integral small fx dx, and again gx was the same thing with respect to small gx dx, and putting these values here I'll get this as integral fx dx plus integral gx dx. So again I just use the basic property that integration is inverse of differentiation. So writing this thing must represent a function, so it will be that the derivative of this function should be this, and again this property also holds, and using simple identities I have proved this relation. So I proved 2. So now get the basic idea of how to proceed where identities of integration are concerned. So okay, now the third property is if f of u du integral is say fu plus c, okay, then integral of f au plus b du is 1 by a f of au plus b plus constant, and obviously a should not be equal to 0 here. So you can see here that to prove this, all you have to do is assume that au plus b is say t. Then differentiating both sides, you will see that a du plus 0 is equal to dt. So instead of du, I am going to substitute it as say f first, this is t, and du becomes dt by a, and this is nothing but 1 by a integral ft dt. But what do we know about this? We are already given that fu du is capital Fu plus c. This is 1 by a capital F and t plus c. Now replacing the value of t, this gives us 1 by a f au plus b plus c. So you can see here that if a function, linear function of u is given in the main, that is instead of fu you are given au plus b, then it remains f au plus b divided by 1 by a, that is coefficient of u plus c. So these are the 3 properties that you need to know about integration. basic properties and the proof I have given. Okay, so with this, now let's move on to the basic methods, but first let me show you some examples on integration, some very basic example, so that you are much more clear. Okay, so first we have an example. So to solve this example, all you need to do is think backwards. Say for this example, I have asked you that integration of tan square x dx is what? So since till now all you know is that integration is the reverse of differentiation. So I need to find a function tx, say, such that the derivative of tx gives me tan square x. So recalling the formulae that you, I'm sure, remember from differentiation, so you can see that, okay, this one is easy. We see that sec x was the function, and plus c, obviously the constant will always be there. Sec x is the function whose derivative gives us tan square x. Okay, this one was easy. So let's move on to a bit difficult. Say this one. So we have e raised to x cos x minus sin x dx integral. So what is the function whose derivative is this function? So this one is not that easy that you can just like orally guess, but a little bit of trying, you can see that it is e raised to x cos x, because on differentiating this you will get e raised to x cos x minus e raised to x sin x using the product rule. So this is what is precisely written here. So sometimes, okay, you have to dig a little deeper. So with practice, so obviously you will get to this. So these were two examples. Let me take two more. These two are a little better. So this is example. Let me just write example. So we have here integration 3 x raised to half and 1 plus x raised to 3 by 2 dx. Okay, so this one's a little bit more tougher than the previous one also. So here, to figure out what is the function whose derivative is this, so now you don't know many techniques. So if you knew techniques, you would have substituted and got a function whose derivative you know. But for now, on seeing, you can see that 1 plus x raised to 3 by 2 raised to 2, because derivative of this 1 plus x raised to 3 by 2 derivative is d by dx is 3 by 2 root x into, okay, 3 by 2 root x, nothing else. Okay, so since derivative of this is this, if I take this function, it will be derivative 2 into 1 plus x raised to 3 by 2 into derivative of this thing, which is nothing but 3 by 2 x raised to half, cancelling the 2, I will get the required function, that is 3 x raised to half 1 plus x raised to 3 by 2. So okay, actually with practice you will get to know, but for now it's maybe difficult for you to find out orally. So we will move on to the next topic, which is techniques of differentiation after this last example. This one is a trigonometric. This one should be easy. So this example says that sine 3x cos 2x dx. What is the function whose derivative is this? So first of all, seeing that, okay, directly is difficult to solve. So if you have studied trigonometry, you will see that this thing can be written as 1 by 2 into 2 and 2 sin a cos b can be written as sin a plus b plus sin a minus b. This is identity. I am not going to prove this, but okay, you can refer any book, you will see that, okay, this is an identity. So using this identity, I am going to write this thing here by this gives us sin this plus this is 5x plus sin this minus this is x, okay, and 1 by 2 integral dx. Okay, so we know that since sin 5x, the function whose derivative will be sin 5x is equal to 1 by 5 cos 5x, because on differentiating cos 5x I'll get sin 5x into 5, which will be cancelled by this 5, okay, and by this I'll get, okay, and a negative sign, don't forget a negative sign. On differentiating cos 5x I'll get minus sin 5x, so negative sign is important. So again here also I get a negative sign, minus cos x, and we have 1 by 2 here plus a constant which is always there. So it may be sometimes that I myself forget to write the constant of integration, but you should yourself never forget So maybe in a hurry I have not written, so it doesn't mean that it's not there, it's always there. Okay, so with these questions I hope you get a little bit of better understanding on what integration is. So with the introduction over, let's move on to the next topic, that is methods of integration. Okay, so okay, but first let me list down all the common integrals that you should know before starting. That is, they are assumed in fact that since the derivative of them is known, so by taking the inverse we know the integration of the other function. So I'm going to write down basic formulae. Okay, so you can see by check them inversely, that is, say I'm saying the integration of this is x raised to n plus 1 upon n plus 1 plus constant. So you can check it for yourself that okay, I will differentiate this side, I should get this function. Okay, I'm getting it. N plus 1 will be cancelled with n plus 1 and I will be left with this. And here obviously n not equal to minus 1. Okay, so I'm just going to write these down. Some of them are easy, some may be difficult to comprehend. So I'll give a little bit proof for them. Okay, so writing it, e raised to x dx is again e raised to x plus constant. This is easy. So remember them by heart because they will be used throughout the chapter intensively. A raised to x by ln a plus c. Then we have cos x. It will be sin x plus c equal sin x dx is equal to cos x plus c. Okay, these are common. Then we have sec square x dx is tan x plus c, and we have then we have cos x square dx, this is minus cot x plus c. Okay, then we have cosec x cot x dx is equal to minus cosec x plus c. Then we have sec x tan x dx is equal to plus c, and then we have 1 upon root a square minus x square dx. You can see that this is sin inverse x by a plus c. And then we have dx upon x square plus a square is nothing but 1 by a tan inverse x by a plus c. Okay, you can see if you remember the derivative of sin inverse tan inverse x, that okay, differentiating this will give you precisely this, and so for this. Okay, and then we have, remember the derivative of sec inverse, which is x square minus 1 dx integral is sec inverse x plus c. Okay, so these are for the fundamental, one or two more, but they will require proof. So the one I have written here, so basically 6 and 6. These 12 are very basic, so you can have to remember them by heart. They will be used intensively throughout the chapter, so remember them. Okay, so okay. Okay, so these are the basic formulae. Okay. So I would like to tell you one thing, that in the first example that I took, I by mistake, that was actually not sec square x. I made a very big mistake, that is, it was tan square x dx, and I told you that its integral is sec x. That is my mistake, sec x, which is wrong. Sorry, I really didn't pay attention that time. But actually it had to be solved like, it had to be written as sec square x minus 1 dx. Okay, then split the integral sec square x dx minus integral dx. Okay, and you can see that the only function whose derivative is 1 is x, so it will be x, and the function whose derivative this is tan x, and then there is a constant. Okay, so this is my mistake. So some of you may have thought that what is he doing? So sorry on my behalf, I made a mistake. So okay, with this I've told you the basic formula, and using a little bit of substitution, that was the basically third property, I'm going to prove, say, integral of cot x, tan x, sec x, and cosec x. So let's see these. So first of all, I'm going to write the integral of cot x dx. So as you all know, cot is nothing but cos x by sin x dx. So if I take sin x to be equal to t, then derivative of this cos x dx is equal to dt. So this thing here becomes dt by t integral, which is, as you can remember, the function whose derivative is 1 by t is ln t. So you have to write ln mod t plus c. C is nothing but ln sin x. So this is, like, you can say, a basic example of substitution. We will discuss substitution in much detail, but this was pretty simple, so you don't need to know much theory. So this is the integration of cot x. So this will also be directly used, so remember this also. Okay, so now similarly the same proof goes for tan x dx is nothing but sin x dx by cos x. So here I'll assume cos x to be equal to t. I'll get minus sin x dx to be equal to dt. So this becomes minus dt by t integral, which is nothing but minus ln mod t plus c, which gives us minus ln mod cos x plus c, or in other words, to remove the minus, I'd make it sec x plus c. Okay, so remember this also by heart. Integral tan x dx is ln sec x, integral cot x dx is ln sin x. Okay, these two are done. So this basically also gives you an idea how to use substitution. Okay, seeing that the derivative is present above, so if you take the denominator as a new variable, then derivative of that is already present, so it's easy to integrate. It becomes a more integrable function. Then we have sec x dx, which is nothing but, so here the trick is, so writing it 1 by cos will obviously not help, but what I'm going to do is sec x, so I'm going to sec x plus tan x multiply and divide. Okay, you'll see in a minute that why this is helpful. Okay, dx. Now seeing that if I assume this to be t, that is sec x plus tan x is assumed to be t, then differentiating this, I'll get sec x tan x plus sec square x dx is equal to dt. So taking out sec x common, sec x tan x plus sec x dx is equal to dt. So this is precisely the term that is present in the numerator. So basically having the idea that okay, multiplying, dividing this, the denominator derivative will be generated. That was the main purpose of multiplying, dividing this. So replacing this there, I have dt by t integral, which is nothing but ln mod t plus c, and ln mod t replacing t, which is sec x plus tan x plus c, or simplifying this, you will get ln mod tan x by 2 plus pi by 4. Okay. So this is one, that is sec x, and similar proof will go for cosec x. You can do that for yourself. Okay, so the answer you will get is, of course, cosec x, do the same way, cosec x dx, here instead of sec x you multiply cot x minus cosec x and divide by the same thing, cot x minus cosec x dx. Okay, here the derivative of the denominator is cot x is minus cosec x, cot x, sorry, I am forgetting the derivative myself, it is minus cosec square x, and his is minus, so it becomes plus cot x cosec x, which is nothing but the numerator cosec x, cot x minus cosec x dx is equal to dt. If I assume this to be t, this is equal to t. Again I have integral 1 by t dt, which is nothing but ln mod t plus c is nothing but ln mod cot x minus cosec x and plus c. Okay, this thing on simplification can be written as ln tan x by 2. Okay. You can use trigonometric identity to simplify this. It's your wish which one to remember. So I have written the integrals basically of tan, cot, cosec, sec. These were a little bit complicated. Not directly you can see that what functions derivative will give you these, but okay, with a little bit of substitution you get the answer. So I have not formally yet introduced you to any of the methods. I just wrote down the basic formula and so on. Okay, so apart from them, the one that I wrote, there are a couple more formulae that I'm going to write, so and a proof also. So till now you don't know anything on how to solve, but with this maybe you get a bit of more idea. Then we'll go into formal topics. Dx upon x square plus a square. Okay, so as you can see here, to solve this, a substitution will be helpful. Basically what I'm saying is, so can you suggest me a substitution that will help me solve this integral? So seeing the formula, expression in the denominator, that is x square plus a square, gives us the idea that using a substitution x is equal to a tan theta should be useful. At least it will get rid of the square root. So let's try this. So x is equal to a tan theta. So we have dx is equal to a sec square theta d theta. Okay, put this here. We have dx is written as a sec square theta d theta, and the denominator becomes root of a square plus a square tan square theta, which is nothing but a sec square theta d theta upon a sec theta, and it becomes integral sec theta d theta. And what is that? That is ln mod, as I just wrote, so you should remember that is this, plus c. So now let us replace the value, that is, it is root of 1 plus tan square theta, which is nothing but x square by a square, plus this is x by a plus c. Okay, so a little substitution, seeing that you must have the tentative idea. When you see a square minus x square, put x is equal to a cos theta or a sin theta and so on. I'll write that down in a moment. But to see, okay, the substitution x is equal to a tan theta really helped us out and reduced the unknown integral that was actually very difficult to calculate to a known integral in some other variable, that is sec theta, which we just derived right now a minute ago to be this, and we put the value here. Okay, so now let's move on to another proof. Let's rub this out. So we will see that basically substitution is a very powerful tool, and with more examples it should be more clear to you. Okay, so with this, okay, so I am leaving the proof of this to you, that is x square minus a square under root. You can see that doing the proof, so I don't really need to suggest the substitution, but it's more than obvious that x is equal to a cosec theta or sec theta, which one you like, should be used, and again you will get an integral like cosec theta or cot theta, which you know. So the answer that you should get on solving this is ln x plus x by a, actually plus 1 by a root of x square minus a square mod plus c. Okay, so you can basically remove a also because a is a constant, so ln this minus ln that. Okay, I'm not proving this, you can prove this for yourself, but you can remember this. Okay, the final one is dx upon x square minus a square integral. So this thing can be written as dx upon x minus a, x plus a. Okay, so with a little trick or thinking, you can see that if I multiply and divide by 2a, which can be written as x plus a minus x minus a and x plus a into x minus a, and this entire thing is this. So basically what I've done is I've broken it into two parts, that is x minus a minus 1 upon x plus a and dx, and 1 by 2 is still 1 by 2a is here. So this integral is nothing but ln mod x minus a minus ln mod x plus a, and 1 by 2a is still here, and then there is a constant. So using properties of log, x minus a upon x plus a mod plus c 1 by 2a. Okay, So you can see some tricks. Basically integration, some questions are very easy. You can directly see that okay, I found out that this function is the answer because derivative of this will give me the function that is asked in the integral. But many of the times you will see that substitution, tricks like these, adding, subtracting something and so on, there are various tricks that I'll teach you throughout the course. So one of them is this. Seeing a format like this, a polynomial below, you can do is split it into its roots if it has some, and then add something in the denominator, actually multiply or divide something, so as to form two simpler integrals, I1, I2, which we know, this is ln x minus a, this is ln x plus a, and so we get the answer. So with this, I have finally taught you the basic standard integrals that we will be using throughout. So the questions that I will be solving, I will simplify the integral given into one of these, let's say 15 or 20 of them which I told you, and from then onwards, from that one onwards, it will be a standard integral which you will know the answer to. So I will not solve further. Okay. So with this, you know the basic integrals. So we can move on to the next topic, which is types of integration, methods of integration basically, not types. So we have methods of integration. Okay. So with these examples, you saw me using some of these methods. Basically, the dominant one was actually substitution. So there are three methods that I will be teaching you to solve integration. First one is method of substitution, changing the variable that I used here, cos x equal to t, sin x equal to t, and so on. Second one is integration by parts, which is actually quite difficult, so we'll deal with that later. And the third is using partial fractions to solve integration. So those of you who don't know, no need to worry. I will tell you first what is partial fraction and then tell you how to solve integration using partial fractions. Okay. So after telling you the three methods of integration, so basically let me start with the first. So basically what method of substitution says that if you have a form like this, f gx d, sorry not dx, g dash x d dash x gx, this is, say your integral is somewhat of this form, then what you should do is put gx as a new variable, say capital T, then this becomes f of t, and this implies that g dash x dx is dt. So this thing gets replaced by dt. So now an integral which was somewhat complicated, as you can see there are many terms, is reduced to a simpler integral. So this is what is known substitution. Using this to simplify your integral so that you can solve further. So it is all up to you to find out which variable to substitute and seeing that which will make the problem more easier. Okay. So basically what I'm trying to say is solve as many problems so that you get the idea that okay, in these type of problems sin x should be substituted and so on. Okay. So this is as far as the theory goes. Basically I've told you when we are going to use it. So, and I'm going to tell you some of the standard substitution. You will be knowing them, but still. So if you have x square plus a square or root x square plus a square, what do you substitute? A tan theta or a cot theta. Okay. So knowing trigonometric functions, you get to know a lot about substitution. Again, root x square minus a square or x square minus a square, x is equal to a cosec theta or a sec theta. Similarly for a square minus x square, root a square minus x square, what is it? X is equal to a sin theta, a cos theta. So this is pretty much standard. And then if you have terms like this, root a plus x, root a minus x, or both are present, then the good substitution is x is equal to a cos 2 theta, because 1 minus cos 2 theta and 1 plus cos 2 theta both form, say 2 sin square theta by 2, that is since it's 2 theta, you know the basic idea that okay, these both will get rid of the square root. Okay, so these are the basic substitution. And one more, that is if you have root x minus b and a minus x, then x should be equal to b cos square theta plus a sin square theta. Okay, So this will basically help getting rid of the square root. So we want to simplify the expressions. Actually, these substitution help getting rid of the square root or making the expression less complicated so that we can solve with standard integrals. Okay. So with this, I have told you the basic idea. Let me take a couple of questions so that it becomes more clear. Okay. So here we have a question, a method of substitution. Okay. I'll take two questions so it becomes quite clear. Okay. Substitution. Very important method. Most of the questions asked. Can we solve by substitution? Okay. So we have a question here. Question. Dx upon x plus 1 raised to 6 by 5 x minus 3 raised to 4 by 5. What is this? So since I have taken it under the heading of methods of substitution, so what should we do? Substitute this, maybe the ratio. So since you are new and you haven't solved any problem on this earlier, so let me solve this one, tell you how it is. So seeing that, if I firstly noting that the sum of these powers, that is this and this, turns out to be 6 by 5 plus 4 by 5 turns out to be 2. So if I multiply, that is x plus 1 raised to 4 by 5 into x plus 1 raised to 6 by 5 and dividing by x plus 1 x minus 3 4 by 5. So I have multiplied and divided this term, yields, and obviously rest everything is present. Dx is there. So what I get is x plus 1 squared and x minus 3 upon x plus 1 raised to 4 by 5. So the purpose of doing this was that, seeing that if I differentiate this x minus 3 upon x plus 1, which can in other terms be written as x plus 1 minus 4 upon x plus 1 or 1 minus 4 upon x plus 1, differentiating this 0 plus 4 upon x plus 1 whole square dx. If I write this as t, then dt gives me this. So x plus 1 square is generated and I have already generated x plus 1 square here. So the tip I am trying to give you is, if you have something like this and you see that these two powers add up to be 2, then the best way to do is, you can do one of the two ways. You can either, actually there is only one way. You create the format that I just created here and put this thing, that is this thing as you can see here, as t, which I did. I got this, which is crucial because x plus 1 square is already generated. So this thing here becomes nothing but dt by 4. So dt by 4 integral, and this is nothing but t raised to 4 by 5. Okay, so this is solved. So integral like this gets reduced to integral like this. So there are infinitely many tricks, so I can't cover all of them in the theory. So I'll try to take as many questions as possible. Say this trick, I took a question, so basically you are now aware that if you see something like this, you will be able to, okay, at least tackle it. Maybe it's not the exact same form, but you know a trick or two on how to tackle this type of situation. So now this is reduced to your easy and integrals and you solve it. Okay. So now let me take another question. So like in this question, I left it at the point where I know you would be able to solve it, so that I can take more questions in the specified time. Okay. So another question will be fine, because okay, one question, as you know, doesn't really do much justice. So next question is integral of dx. Now there is a root x minus a d minus x. Okay. So in the theory only I told you that seeing this type of expression, the best substitution is x is equal to a square cos square theta plus b square sin square theta. Okay, let's see why this is helpful, because I didn't say why this will help. So let's see. Dx is equal to a square into 2 cos theta minus sin theta plus, sorry, not a square, my mistake, actually it's just a and just b. Okay, plus b into 2 sin theta cos theta, giving it to be sin 2 theta b minus a d theta. Sorry, I forgot to write d theta both times. d theta is dx. Okay, so substituting this here, we have d theta, which is sine 2 theta b minus a, and the denominator is root of x minus a, turns out to be a sine square theta plus b sine square theta into, next time b minus x turns out to be a cos square theta, which is minus b plus, look, 1 second, let me write this clearly, maybe I'm making a mistake, so just to be clear. So we have x minus a, so x is, which is a cos square theta plus b sine square theta, so minus a leads to b sine square theta minus a sine square theta. Okay, and b minus x is b minus a cos square theta plus b, sorry, not plus b, minus b sine square theta, which gives us b minus a cos square theta, which gives us b minus a sine square theta. So multiplying this and taking the root, I am left with b minus a sine theta cos theta. Okay, so b minus a cancels out, so I am left with integral. So in this question, it turns out that using this substitution, which I told you in the theory, turned out to be pretty useful and reduced our integral into nothing but 2 times d theta. Okay, and so to calculate this, which is actually 2 theta plus a constant, we see that, okay, from this b minus x upon b minus a and the root is cos theta, or this implies theta is nothing but cos inverse root b minus x upon b minus a. So initially, if I hadn't told you the substitution, so the question was basically pretty hard, as you can see, but a substitution, which is this a cos theta plus b sin theta, reduced the question into pretty easy question. So try to remember in your mind all these substitutions that I am taking through examples, so that in the future you are able to use them. So let's move on to the next question, okay, which is also on substitution, but a little trickier. So that will also help you understand more on substitution. Okay, so the next question that I'm going to take is this question. Okay, let's grab this. Is integral root x upon root of x cube plus a cube dx. Okay, so since I've already given you the hint that it's on substitution, so try to think for yourself what substitution will help us. Maybe, as you can see, as I told you, if there is a root sign, maybe you think that taking x is equal to a what 1 by 3 tan 1 by 3 theta will help. No, not actually. Okay, this, because on cubing this, so we will have x cube is equal to a cube tan square theta, and then adding a cube, and maybe you will get something. I haven't tried this way, so you can try it for yourself. But the substitution which I could think of for this question was, seeing that there is root x in the numerator, and whose derivative gives us root x. We see that d by dx of x raised to 3 by 2 is nothing but 3 by 2 into root x. Okay, so if I substitute x raised to 3 by 2 as t, what I get is 3 by 2 root x dx is dt. Okay, so substituting this root x dx as 2 by 3 dt, and the denominator becoming as it's x cube is nothing but t square, so t square plus a cube, so it gives us 2 by 3 integral dt upon root t square plus a 3 by 2 square, and you know this integral, so I'm not going to solve it. So the integral, which was this, and seeing that though, so let me rephrase it, the basic trick that I'm using here in this type of question, specifically this one, is that the numerator I am finding a function whose derivative is the numerator. So with this process I found out that, okay, x raised to 3 by 2 is the function whose derivative is root x. and seeing that okay, the denominator is also a function of x 3 by 2, that is t square plus something. So it turns out to be that using this substitution helped me. So the general form here is, if you have say fx into gx or fx by gx, where the integral of fx, basically integral of fx is present in gx, that is gx can be written, gx is a function of integral of fx. So as you can see, integral of this was actually this, actually x raised to 3 by 2 was nothing but integral root x dx, x raised to 2 by 3, as you can say that. So integral of root x was something x raised to 3 by 2 times something, and we see that the denominator of the other function was a function of this x raised to 3 by 2. So in these type of situation where this condition is followed, that is one function's integral is present in the other function, that is the other function is written as a function of integral fx dx, then the substitution that integral fx is t dx gives us fx is equal to fx dx is nothing but dt. So with fx dx we get dt and t becomes here, so fx by gx becomes fx dx becomes, this becomes dt upon say L of t. Okay, so because gx was a function of integral this, and integral this is nothing but t, so it becomes t or small t. Okay, so with the example I try to give you the idea, so it's up to you if you are able to remember, or at least get to see why I am doing the things that I am doing, because that's very important in integration. All you need is an instinct to see what to do to which question. Okay, so now let me take another example. This one's easy if you know trigonometry, if you remember that. This is sin x plus cos x upon 9 plus 16 sin 2x dx. Okay, so this question also is using the same trick that I used in the previous question. So as a hint I am telling you. So here also you can see that the denominator is actually a function of derivative of this or integral of this. So we see that sin x plus cos x dx integral is nothing but, it is actually minus plus sin x, sorry, if its integral is t, then times dx is equal to dt. Okay, but the denominator, which is 9 plus 16 and sin 2x, can be written as basically we have sin x minus cos x whole square is nothing but 1 minus sin 2x. So sin 2x can be written as 1 minus sin x minus cos x whole square. So substituting this here, we have 9 plus 16 times this, which is 25 minus 16 times sin x minus cos x. Okay, and this is nothing but sin x plus cos x dx, this squared. So seeing that, okay, if I write this function as t, I have this as derivative of t, that is if I have sin x minus cos x as t, then cos x plus sin x dx is dt. So it's you can skip this part, this is also another explanation, but the basic idea, as you can see without the hint everything, is that just writing sin 2x in the form of sin x minus cos x and seeing that the thing present in the numerator is actually what will be obtained if we take this as t, and so this is what is in the numerator times dx is equal to dt. So this question is easily reduced to dt upon 25 minus 16 t square, which can be written as the formula ln x minus a plus a, so on. You know this. So with the substitution, you can remember the general form that whenever sine 2x is in the denominator, so you can generate terms like sin x plus cos x or sin x minus cos x. So if there was, say, sin x minus cos x, then we could have, and say something 9 plus 16 sin 2x, then we can also have written that sin 2x, actually let's rub all this. So what I'm trying to say is, we have sin x plus cos x derivative is cos x minus sin x. Okay, so since this is present in the numerator, so we can write sin x plus cos x whole squared is nothing but 1 plus sin 2x. So sin 2x can be written as 1 sin x plus, sorry, I'm messing it up, can be written as sin x plus cos x whole square minus 1. So putting it here will give us sin x minus cos x dx upon 9 plus 16 sin x plus cos x whole square minus 16. So the derivative of this is present here with a negative sign. So basically you get the idea that transform the denominator in such a way that by substituting a part of it, the derivative is present in the numerator. That's the key trick in substitution, that you have to generate the derivative in the numerator so that it cancels out and you are left with the easier term. So with these examples, I've tried to explain it to you. So okay, we have finished this part. So there are a couple of subtopics left, that is some special type of integrals, say some are known as algebraic twins. That is integrals of the form, say 2x square upon 1 plus x4. Okay, I is this, but it can be written as x square plus 1 upon 1 plus x4 plus x square minus 1 upon 1 plus x4. So we can solve these separately and tell you how to solve this. I'll solve one of them, so you'll get the idea. Okay, and similarly, if I had 2 upon 1 plus x4, then I could have written it as x square plus 1 upon 1 plus x4 minus x square minus 1 upon 1 plus x4. And again, so if you know integral of this, so you can find integrals of this. So this is known as twin integral. And similarly, you can solve for 2 upon x4 plus 1 plus kx square if it is present. And similarly for 2x square upon x4 plus 1 plus kx square. Okay. So this is a general idea. I'll tell you how to solve this. I'll take it as an example. Okay. So let me solve one of these so that you get an idea. This is very important. It occurs very frequently. So let's take the question this. So we have a question 5 upon 1 plus x4 integral. Okay. So as I told you, I'm taking 5 out, multiplying divide by 2. So to get 1 plus x square upon 1 plus x4 minus integral x square minus 1 upon 1 plus x4. Okay, so let's solve both of these so you get an idea. So first of all, I have 1 plus x square upon 1 plus x4. What I'm going to do is, I'm going to divide by x square. So I have 1 by x square plus 1 upon x square plus 1 by x square. Okay, so trick here is that 1 plus 1 by x square, and this thing here can be written as x minus 1 by x whole square plus 2, because if you open this, you will get x square plus 1 by x square minus 2, and plus 2 will cancel this. So seeing that the derivative of this is 1 plus 1 by x square, which is present here. So substituting this as t gives us this times dx is nothing but dt. So a question like this, by using certain steps, dividing by x square and then making this a perfect square, and seeing that its denominator is present, its derivative is present in the numerator, gives us that this times dx, actually dx was here the entire time, dx integral dx. So I am solving, say this is I1, so I am solving I1. So I get I1 to be, after substitution, this is nothing but dt upon t t square plus 2, which you can write it as 1 by root 2 tan inverse t by root 2 plus constant. In a similar way, you can write I2 also. So if this is I2, so I am saying that I2 can also be written as 1 minus 1 by x square upon x square plus 1 by x square. But here the trick is, here I formed the square of x minus 1 by x plus 2 because its derivative was present. But here, since the derivative of x plus 1 by x is present, because its derivative d by dx is 1 minus 1 by x square, so I am going to write this as 1 upon 1 this upon x plus 1 by x, x plus 1 by x whole squared minus 2. So you get a plus 2 and minus 2, and this is dx integral. So it becomes, if I substitute this, obviously this is t in this case, so I have integral dt upon t square minus 2, which can be written as ln ln mod x minus a upon x plus a, and so on, whatever the formula is. So basically, an integral like this is firstly broken into two, solved individually. This is x minus 1 by x square, here x plus 1 by x whole square, derivative is obviously in the numerator already. So this is pretty standard substitution that you should know. So I have taken this as an example. So this is generated various times in trigonometric also. Say I am going to take an example to see when these twins, as you call them, are generated in trigonometric integrals. Okay. So trigonometric integrals, let me take this. Okay. So you have 4 upon sine 4x plus cos 4x dx. Okay. So if I say multiply by sec 4x and multiply here, so it becomes sine 4x sec 4x plus 1 dx. Okay, this becomes 4 times sec square x 1 plus tan square x, and this is nothing but tan 4x plus 1 integral dx. So now you can see that if I take tan x to be equal to t, I have sec square x dx to be equal to dt. So this we have 4 1 plus t square upon t4 plus 1 dt, and you can solve this accordingly. It is 1 plus t square, so there is only one integral, divide by t square on both on numerator and denominator, and you will get the answer that we just proved. So you can see that certain trigonometric substitutions also lead to this algebraic twin. So knowing its formula directly, at least for objective parts, or at least knowing how to approach it, helps us in solving various other problems. Okay. So I told you about the algebraic twin, which occurred in both actually trigonometric as well as directly in algebra. So after that, what I'm going to tell you is the next topic. Basically, with these examples and all, I hope I have covered how to solve integration using substitution, though no amount of examples are actually enough for perfect understanding. But with these examples, I have covered basically the foundation, so that now you can solve examples with your own instincts. That is, when is to substitute x as a tan theta cos theta, a cos square theta plus b sin square theta, and so on. So with this, I have finished the first method of solving integration. So let's move on to the second part. This is also quite important. So that is integration by parts. So second part is integration by parts. Okay. Integration by parts. Okay. So basically, it's a method to split an integral. Say if you have integral of fx and gx into two other integrals, which are basically, I'm going to write it down. So we have integral uv, u and v are functions of x dx, u, v comma u are functions of x. Okay, so this is dx obviously. So this thing can be written as integral. Firstly, you have a function outside v dx minus integral du by dx integral v dx and dx. So this is the formula of integration by parts. That is, given two functions integral, you can write this as u integral v dx minus du by dx into v dx integral and the entire integral. So to see why this is correct, so let me rearrange it. So taking this side, we see that uv plus du by dx integral v dx is u integral v dx. Okay, so what I'm trying to say is that this is the identity. By rearranging, I've got this. So to see whether it's true, differentiate both sides. So you'll see that derivative of this is uv plus du by dx integral v dx, and derivative here is du by dx integral v dx plus uv, which is basically true. So what I'm trying to say is the by parts formula actually is derived from product rule of differentiation. That is, since the using product rule of differentiation gives us this, that is d by dx of this function is nothing but this function. Okay, so on integrating this, we get this side should be equal to this side, so which is precisely the result we have written, but taking this term which was on the left hand side to the right hand side to get a good formula, that if two functions are given as dx, so you can express it as this and see whether the two integrals are relatively easy to solve compared to the first one. Okay, so this is the formula, integration by parts, and we'll see that it's very useful to calculate some of the integrals that are obviously difficult by substitution. So let me first tell you about certain aspects of integration by parts. So this function here is called the first function first, and this here is called the second. Okay, so by the formula itself, you can see that our basic approach here should be that since this integral itself is difficult to calculate, so what we are going to do is we are going to use this formula, but we are going to choose u and v such that the integral of v is easy compared to the integral of u. Otherwise, if u integral is itself difficult, so what's the purpose of using by parts? Because again we'll be stuck here. So out of u and v, whichever integral is relatively easier, that one is going to be v, because in the formula integral of v is used, and the other one whose integral is tough will be u. So following this, some rules have been created. That is, generally the ILATE rule, which is anagram for acronym anagram, I don't know the word, that is inverse log algebraic trigonometric and exponential. By inverse, I mean inverse trigonometric, obviously. Okay, so this is the order that should be followed. That is, if say these two functions are present, log and trigonometric. Okay, so this should be the first function, this should be the second. That is, whenever two functions are present, so the one which is in the left of this, actually say algebraic and exponential, these both are present. So to see which one will be the first or second, the one on the left in the sequence will become the first, and the on the right will become the second. Generally, it has been found out that this approach usually results in a much easier integration compared to the previous one. So that is why it is well known, and so everyone tells the students, okay, if possible follow this. So okay, I've told you, so remember this. Sometimes though it may not be that useful, but 90% of the time this will help you, that inverse. So you can see that the integration of this is very easy, exponential. Trigonometric is also relatively easy. Algebraic is somewhat difficult certain times. Log is very difficult, and inverse trigonometric are absolutely very difficult. So with the relative hardness increasing this side, it is preferable to make these functions on the left to be u, so that we don't have to integrate, just differentiate and keep constant, rather than the function on the right. Okay, so here also I have written that inverse trigonometric functions should never be used as v, because we don't know their integrals that much easily. So and okay, so basic idea here is how to choose function. That is the basic funda that you should know on integration by parts. So I have told you the ILATE rule, so that pretty much covers it. So let me take some questions so that you know, okay, which one to prefer as a first and second. So this is also very important technique. Certain integrals I will be proving with the help of this. So okay, so let's take basic question ln x integral dx. So seems to be very simple, but if you try to think orally, you will not be able to find, okay, which function is there whose derivative comes out to be ln x, and neither you can think of a substitution that will help. So here in these type of situation where neither the substitution nor the basic fundamental principle helps you to find the integration is when integration by part comes in to rescue you. So seeing this, and one more thing I'd like to tell you, that if there is only one function, which is the case here, you can assume, say, 1 dot this, 1 can be assumed as the other function, okay. So using by parts, using integration by parts, I am writing 1 dot ln x as, so this is obviously going to be my first function first, this is second, okay. So first function stays outside ln x, then integral of this, which is 1 dot dx minus integral ln x derivative is 1 by x into integral 1 dot dx and dx, okay. So this is what I will get assuming this first second. So on opening, I have ln x dot x minus integral 1 by x dot x cancelling out dx gives me ln x minus 1 times x plus obviously a constant there. So you can see that here we've got the answer very easily by integration by parts, selecting very efficiently and very carefully which is to be first or which is to be the second, okay. This was an easy example just to get you in the feel of integration by parts, okay. So let's take a hard example, say that will, so there, okay. So this is the second example. So integration of root x square plus a square dx, okay. So as I told you, when you see this, useful substitution is x is equal to a tan theta, but you can try it for yourself. In the middle only you will get stuck, then you will have to use again integration by parts. So I am directly using integration by parts in the beginning only. So though you can try it for yourself, okay. So as I have already told you, we will be using integration by parts. So obviously we will assume 1 as the second function. So this is the first function, first, and this is second. So again applying, we have root x square plus a square remains there, integral 1 dot dx minus derivative of this, which is 1 by 2 root x square plus a square into 2x dot integral of 1 dot dx and then dx, okay. You can write it as this, okay. So this is x root x square plus a square, this cancel out, this becomes x square upon root x square plus a square dx. So this part is solved, we just need to solve this. So to do this, what I do is x square plus a square upon root x square plus a square plus a square upon root x square plus a square, okay. I have subtracted a square, added a square so that it's nullified, and this is obviously here as it is, it comes out to be here. So we have this thing again becomes integral root a square plus x square, okay. This thing, this cancels out to being root this. So I'm taking it on the left hand side. So I have 2 times I now is equal to x root x square plus a square 1 by root x square plus a square, okay. So this is what I get. So dividing this by 2, I have x by 2 a square by 2 and integral of this, which I am directly going to write as I don't remember what it is. So integral of this comes out to be x by 2 root x square plus a square, I am writing the first part, plus a square by 2, and this integral was supposed to be ln mod x plus x by a plus x square plus a square root by a plus a constant, okay. So what actually happened here was using, okay, the 1 to be the second function, this to be the first function. I used integration by parts, applied the formula. Remember the formula correctly, don't confuse it. Okay, whose derivative we have to take, whose integral we have to take. Do at least 10-15 questions on integration by parts to just remember the formula correctly, apply it very fast, don't have to think that much. So I got this. This one was easy and this was seeming to be difficult. But seeing that adding a square and subtracting a square results in two integrals, one is actually I itself. So I took it on the left hand side, I got 2i, and this was integral which I had already proved in the very beginning of the chapter to be x by a plus this. So we have 2i is equal to this, so I divided by 2 to get x by 2, a square by 2 this plus a constant. Okay, so whenever, obviously substitution could have worked, but according to me it does not. So whenever you are stuck seeing that okay, I am not able to think of a substitution, always try by parts following the isolate rule, and maybe you get the integration to be a little simplified than the initial one that you had. So it's worth trying out. Okay, so let me take one more example on integration by parts, a good example. Then I'll tell you some other tricks, some not related to integration by parts but separate. Okay, so we have sec cube theta d theta. Okay, so as I've already told you, we are going to be using integration by parts. So let's see. So this thing here is, say, sec square theta sec theta d theta. So if I take this to be the, actually this to be the first function, first, and this to be the second, because I know okay, tan theta derivative, actually sec square theta d theta integral is tan theta. Okay, so using the fact that this integral is relatively easy as compared to this, I am giving this the second and this as first. So using by parts, what I get is that sec theta will be outside, integral this will be, that I have to calculate, minus, then I will have derivative of sec theta is nothing but sec theta tan theta, okay, into integral of this sec square theta d theta, and then after this finally a huge d theta. Okay, so till now, okay, this integral I know, so this part's easy. We have tan theta sec theta minus, what's this part? This part is, on simplifying, this is obviously tan theta, this integral here is tan theta, so I have sec theta tan square theta, which is nothing but sec square theta minus 1 d theta, so it again becomes tan theta sec theta minus integral sec cube theta plus integral sec theta d theta. So again this is what, this is again I, so okay, this time also again I is formed, so we have 2i is equal to tan theta sec theta, actually I is equal to, let's take the 2 this half time integral sec theta d theta. So now you remember the integral of sec theta, I am going to directly write it down. Let's see what this comes out to be. So we have the answer here as solving this. Okay, its integral is nothing but tan theta sec theta plus half times ln mod sec theta plus tan theta. Okay, this was easy, I should have remembered this. Okay, but you should remember all these. As you see that it simplifies to smaller integral sec theta, cosec, tan, cot. Remember them by heart, so no time is wasted in the exam for proving these little things. Okay, so as you can see that I could have taken one as the first function, sorry, as the second function, and this to be the first function, but maybe that would have not helped that much. Seeing that okay, sec square theta is also pretty easy to integrate, so this helped me get the answer easily. So this all is because of practice, that you get to know which function, if there are 2 or 3 choices available, which one is the best. Seeing it orally that okay, this will cancel out this and so on. So practice, maths is all about practicing. Okay, so I have covered a couple of examples on integration by parts. So I'm just going to tell you a trick here. This is also very common, you will see that if you have integral of the form e raised to x fx plus f dash x gx, sorry, not gx, dx. So this is directly actually e raised to x fx plus constant. As you can see, derivative of this is nothing but this. So sometimes you can see that if you have e raised to x gx dx, manipulating gx to writing it as fx plus f dash x using something, adding something, splitting, using actually partial fraction, you can say that, splitting it over to generate this can be very helpful. So the integral will be solved in a couple of lines. So seeing e raised to power x should actually give you a hint to at least try to split the remaining function into something. Maybe you succeed. If you don't, then use your general approach, substitution and so on. Or by parts. By parts is also very useful with e raised to x, this being very easy to integrate. So it becomes the second function and gx is basically the first. So let me take some example to show you how this form is generated. Okay, so this is a trick that you can remember. Okay, seeing e raised to x should hint you towards this. Okay, so sometimes, okay, the simple examples are say e raised to x, 1 minus x minus 1 minus x squared dx. So this is, I have written it explicitly. Someone may write it as x minus 1 upon x squared, so you don't realize spontaneously, but it is e raised to x by x plus c. Again, say e raised to x sin x plus cos x. This is written explicitly. Maybe I could have written it as say maybe cos x e raised to x 1 plus tan x dx. Okay, so seeing this does not recall that this is equal to this and which is equal to e raised to x sin x plus c. So one will obviously not give it to you straight away that okay, e raised to x fx plus f dash x. He will manipulate, maybe use some trigonometric identity to simplify 1 plus tan x and so on. So it is actually difficult to find out sometimes it's easy. So I'm just writing examples. So let's do a question where it will be not given that directly. Say this question. We have e raised to x and actually 1 minus x upon 1 plus x square dx. Okay, so obviously I am taking it under this section, so it will be using this. So obviously you can see directly nothing is given. So let's see. Okay, so we have solving this, it's whole square now. Okay, so we have 1 plus x square minus 2x upon 1 plus x square whole square e raised to x. Okay, so this is also relatively easy. You can see that on opening this I get 1 upon 1 plus x square minus 2x upon square whole square. So if this is fx, this thing with plus and negative sign, this is f dash x. So sometimes, okay, here it is easy to see, okay, differentiating this will give this. Or if this would have been a little bit complex function, to see that the derivative is written alongside it was turns out to be pretty difficult. That okay, you may make mistake on calculating derivative and you see that okay, it does not match. So that's also a problem certain times. But here it was easy, seeing that okay, so the answer is e raised to x upon 1 plus x square plus constant. And just a little example to show you that these tricks are also important. With this example, we came to the end of our second topic, basically, that was integration by parts, second method of integration. So now you know two methods of substitution and integration by parts. Now it's time to move on to the third method, which I told you about, which was integration by partial fractions. So we have integration by partial fractions. So first let me define what is the method of partial fractions, and then you will automatically get to know that why it is helpful. Okay, so basically if we have px upon qx, where obviously px and qx are polynomials of x. Okay. So the method that I am going to tell is that if degree of px is less than degree of qx, then if qx is x minus a raised to k x square plus alpha x plus beta raised to p and so on. That is, it has terms like this, x minus a1, x minus a2 and raised to various powers and terms like this. Okay, so then what we do is, and so on. Okay, so what we do is we write px upon qx as a1 upon x minus a1 plus a2 upon x minus a2 whole square, a1 whole square, plus a3 upon x minus a1 whole cube, and so on till ak upon x minus a1 raised to k, plus say b1 plus x c1 upon x square plus alpha x plus beta, similarly plus b2 plus x c2 upon this thing raised to 2, and so on. So for each and every term like this raised to k, we write k terms 1, 2, 3 and k constants, obviously a1 to ak to b1 c1 so on, all are constants. So the method, actually the theory of partial fraction, says that if you have a condition like this, degree of px is less than degree of qx, so and qx is represented as this product of x minus ai raised to k and x minus a2 raised to k, b2 c2 and so on, a2 a3 a4 a5 and so on, terms like this also. So all you need to do is write it as this and use any method, that is, say, to find the values of a1 a2 a3 a4. Usually what we do is we cross multiply the entire thing, so the denominator becomes qx itself, so qx cancels out, so we have px on cross multiplying, px is equal to a1 something something x plus a2 so on plus this, and we put values of x to get relations in the variables, in the constants which are now unknowns. And so if we have, say, t variable, so we will put t different values of x to get t relations and use system of equation, matrices, determinants, whatever to solve. But generally the questions that we are dealing with will not have so large powers, because it becomes tedious to calculate so many equations, so many unknowns. So generally we will have like 4 or 5 at max variables, unknowns to calculate, which can be done by suitable values of x, so that at least 2, 3 get cancelled out, 2, 3 vanish, and then we get simpler equations. Okay, so this is basically the theory of partial equations. Partial fractions. Okay, so here the initial condition that I told you, that degree of p has to be less than degree of q. If that is not followed, then you know that you can divide px by qx to give, if degree of px is greater than equal to degree of qx, then px can be written as something, say rx plus tx by qx, where obviously degree of tx is less than degree of qx and rx is polynomial in x. Okay. So generally if px has a greater degree, so what you do is nothing to worry about, divide it using a normal division, we'll get a polynomial in x. So this can be integrated easily, so px by qx is actually can be written as this plus this. Okay, so this is integrated easily, and this is then integrated using partial fractions. So this is another case that you should know, that partial fractions can be used. So this is basically the definition of partial fractions. Let me take a question so that you understand, okay, how do we write partial fractions. So say if someone asks you question, integral of x plus 7 dx upon 2x minus 3 3x plus 4. Okay, so the method says that since degree is smaller than this, so no problem, so we say a1 upon 2x minus 3 plus a2 upon 3x plus 4. So this thing, this expression, actually this rational function can be written as this. Okay, integral this dx. Okay, so all we need to do is find a1 and a2 and we'll get our answer, because this is simple. This is 1 by 2 ln of this, 1 by 3 ln of this. Okay, so how do we find a1, a2? So first of all, we know that a1 into 3x plus 4 plus a2 into 2x minus 3 upon 2x minus 3 into 3x plus 4 is x plus 7 upon the same thing, that is 2x minus 3 3x plus 4. Okay, so the pen is getting a little light. Let's change it into say this. Okay, so with this cancelling out this, what we have is a1 3a1 plus 2a2 times x plus 4a1 minus 3a2 should be equal to x plus 7. So we know that 3a1 plus 2a2 has to be equal to 1 and 4a1 minus 3a2 has to be equal to 7. Okay, so we can see that a1 should be equal to 1 and a2 should be equal to minus 1, satisfy this solution. So I've seen it orally. You can solve it by normal methods that you do. So this gives us that 1 upon 2x minus 3 minus 1 upon 3x plus 4 dx is our answer, which is nothing but 1 by 2 ln mod 2x minus 3 minus 1 by 3 ln mod 3x plus 4, and again a constant. So basically, seeing this general format should generally strike in your mind that okay, partial fraction should be used. Be careful in solving this, find a1, a2. Here it was simple, 2 variables only. Maybe it would have been a third one here also. Then it would have been 3 variables. So it can vary according to difficulty, but the method is very good in solving these particular types of problems. Okay, so partial fractions, a third and last method, standard method actually, there are other tricks also. Okay, so let's do a proper question. Okay, so we have a question here. It says x upon, this is also easy, so is 2 x plus 5 dx. Okay, so we have this. So again, what I'm going to do is a1 upon x minus 2 plus a2 upon x plus 5 integral dx. Okay, so sometimes one can orally find out these a1 and a2 just saying okay, I can add this, subtract this, so it will get splitted, but it is safe to do this way. It ensures that okay, you're doing the right step. So we have a1 x plus 5, I am skipping a step, just directly equating the numerator to x. So we have 5a1 has to be equal to 2a2 because constant term is 0, and a1 plus a2 has to be equal to 1. So a1 has to be equal to 2a2 by 5 plus a2 is equal to 1. This implies a2 has to be equal to 5 by 7 and a1 is to be equal to 2 by 7. So very easily I get a1 and a2. So this gives us a1 is 2 by 7, integral gives us ln mod x minus 2 plus a2 is 5 by 7 ln mod x plus 5 plus c. So another easy example just to show you how it is done. So now let's take an example with a higher degree in the denominator so that you know that as well. Okay. So here I have x upon x cube plus 1 dx. So okay, so as I told you, I am taking an example with a higher degree. Usually I was taking quadratics, so now I have a cubic. So let's see if we are able to split it. So we know that the formula x cube plus 1 is x plus 1 x square minus x plus 1. So let's just check it if it's alright. X cube plus x square minus x square minus x plus x plus 1. This cancels with this. So this is the formula. Okay, we can split with this, and this, as we know, has no real roots. So we are going to write it as it is. So we have x upon x plus 1 x square minus x plus 1. So this is the other case that I was telling you about. Terms like this which can't be further splitted into say two linears. So to use partial fraction in this, we have a1 upon x plus 1 plus a2x plus a3 upon x square minus x plus 1. Okay, this is what we use. So cross multiplying, we have a1 x square plus a1 minus a1x plus a2x square plus a2x plus a3x plus a3. Denominator gets cancelled, should be equal to x. So this tells us a1 plus a2 has to be equal to 0. So this gets cancelled out. Constant term should also be 0. That is a1 plus a3 should be equal to 0. This gets cancelled out, and a2 plus a3 minus a1 has to be equal to 1. So since a2 is nothing but minus a1 and a3 is also minus a1 is equal to 1, this gives us a1 is equal to minus 1 by 3. So a2 is equal to a3 is equal to 1 by 3. So we have this is equal to a1 1 by minus 1 by 3 x plus 1, and this is plus 1 by 3 x plus 1 upon x square minus x plus 1. So you can check it just to be sure. So taking out 1 by 3 common, we have x plus 1 square minus 1 upon x square minus x plus 1. So sorry, not this. So we have 2x square minus x plus 1. Okay, sorry, my mistake. So this is, so on seeing, we have 1 by 3 x square plus 1 plus 2x minus x square plus x minus 1. So this cancels. This gives us 3x and 3 cancels. So okay. So I have just verified okay the calculation we have done, just to be sure that you are on the right track. Always just quickly check it in the rough side that you get the function this on putting the values of a1, a2, a3 and then cross multiplying. So finally, with this all done, we are left with two integrals which are basically this minus 1 by 3 times 1 upon x plus 1, which is easy because it's just ln, and plus 1 by 3 times x plus 1 upon x square minus x plus 1. Okay. So this one is easy. This is nothing but minus 1 by 3 ln mod x plus 1. So what about this one? This one that you see here is, there is a standard way of solving this. That is, if you have this form, I'll tell you just a time later in a other topic on how to solve generally this, but it is x plus 1 can be written as derivative of this, which is 2x minus 1 t times this, t1 times this plus t2 times. Okay, so on equating we have t1 is equal to half and t2 is equal to minus half plus half. Okay, so x plus 1 can be written as half times 2x minus 1 plus half, and it is divided by this thing x square minus x plus 1. So basically what I have done is I have written this as a linear combination of derivative of the denominator plus some constant. So it turns out to be this. So if I write it as two separate integrals, first of all it will become ln of this because its derivative is present here. So by substitution you can solve this. And the second part on making perfect square, that is second part, let me just rub this all out so then I can write it clearly. So basically the first part is 1 by 2 times 2x minus 1 upon x square minus x plus 1. Okay, integral dx. This is first, this is easy. Use substitution. Substitute this dash t and you will get 1 by t dt, and this will turn out to be whatever. So second term is 1 by 2 dx upon x square minus x plus 1. This can be dx upon x minus half whole square plus actually minus plus 3 by 4. 3 by 4. So you can see that okay, it becomes the form of tan inverse. So tan inverse, this is substitution, first part was ln. So basically okay, this is somewhat lengthier than normal because degree is 3, so 3 variables, so calculating and 3 integrals are formed, but okay, still you can handle it, so no problem there. Okay, so like I told you, partial fraction is also pretty easy, though a lot of integrals are involved finally in the final answer, but each of them is easy to evaluate. Okay. So there was example on partial fractions. So now moving on, we have next. Okay, so a general question with the case that degree of P is greater than degree of Q. Like I told you that in such a case we need to divide p by q to get a polynomial in x plus another polynomial which has degree smaller than q. Okay, so let's do an example on this. So to be clear, so we have question x4 minus 3x square plus, not plus, it's negative sign, minus 3x minus 2 upon x cube minus x square minus 2x dx. Okay, so let's divide it. So we have x cube minus x square minus 2x divided x4 minus 3x square minus 3x minus 2. So first of all we have x4 minus x cube minus 2x square, so plus, this is minus, plus, plus, so this gets cancelled out. We have x cube minus x square minus 3x minus 2, so plus, minus, actually plus 1, okay, plus 1, we have x cube minus x square minus 2x minus plus plus, so this cancel out, this cancel out, we have minus x minus 2. Okay, so we have this. Okay, so we have that x4 minus 3x square minus 3x minus 2 can be written as x cube minus x square minus 2x into x plus 1 minus x plus 2. Okay, so dividing by this, dividing by x cube minus x square minus 2x by x cube minus x square minus 2x by x cube minus x square minus 2x, which is the required, this gets cancelled out, so we are left with integral x plus 1 minus x plus 2 upon x cube minus x square minus 2x dx. So like in the previous section I told you, this is very easy, this is just basic integral x square by 2 plus x, and this can be solved, that is x plus 2 upon x cube minus x square minus 2x is nothing but x plus 2 upon taking out x common, x square minus x minus 2, which is nothing but x minus 1 x plus 2, one second, minus x, okay, other way around, x plus 1 minus 2, okay, minus x, okay. So this thing can be written as a by x plus b by x plus 1 plus c by x minus 2 is nothing but x plus 2 upon x, x plus 1, x minus 2. So cancelling this out, we have a x plus 1, x minus 2 plus b x, x minus 2 plus c x, x plus 1 is nothing but x plus 2. So put the value of x equal to 0, so you will see that a into 1 into minus 2 is equal to 2. So this gives us a is equal to minus 1. So similarly you get the value of b and c and put it here and integrate, you will get 3 terms of ln, ln this, ln this, ln this, and so you are done. Basically you know this, and so the problem reduces to a very easy problem. So remember the two cases. If you have the degree of this is greater than this, always remember to divide carefully and then reduce it into a problem of partial fractions. If it is already given that the degree is low, so start by using partial fraction and proceed onwards. Okay. Okay. So let's do another example. Okay. So we have this, I'm just going to give you an idea. So if you were given like say this, x upon x minus 1 whole cube into x square plus 2 dx. So since the first condition is satisfied, the degree is already less, so there is no need to divide. So I am just going to write it. This should be written as a upon x minus 1 plus b upon x minus 1 squared plus c upon x minus 1 cube plus dx plus e upon x square plus 2. So here you have 5 variables, so it will be quite difficult to calculate, but if something like this was asked, calculate a, b, c, d, e, and obviously these 3 are easy to calculate, and this also you can write, say if say d comes out to be 1, e comes out to be 1, So you have x plus 1 upon x square plus 2. So write this as x upon x square plus 2 plus 1 upon x square plus 2. This is tan inverse 1 by root 2 x by root 2, and this is, say, multiplying and dividing by 2, 1 by 2 ln mod x square plus 2. So whatever the case this may be, 1 will turn to be tan inverse 1 ln of this, and so you can handle it. Okay, so this is a much bigger example for you to tackle if you want to solve it. Okay, so with this example that I just did for you, we have come to the end of our third standard method of solving integration, that was integration by partial fractions. So with this I have told you the three basic methods that should be with which you should be able to solve all the problems of integration with a little bit of intuition, that is substitution, integration by parts, and integration by partial fractions. Now I'm going to discuss with you some of the standard formats that are used, say, for algebraic integrals, trigonometric integrals, and irrational integrals. That is, given a standard form that I'm going to write, say, if this form is given, what should be your approach? If this form is given, what should be your approach? And then I'll take some questions so that you are familiar with, okay, how to approach this. Okay, so by now I hope that you have understood all the three methods that I taught you. So okay, so the next topic is algebraic, algebraic integrals. So in this I'm going to tell you that if a general form is like this, ex plus q upon root ax square plus bx plus c dx is given. So what should be your approach? So your approach should be that, okay, if I am able to express px plus q as L times derivative of this, which is 2ax plus b plus m, where L and m are unknowns that you will find L and m such that this can be written as this. So if this becomes, we have L times 2ax plus b upon root ax square plus bx plus c dx, obviously. Sometimes I forget to write dx, so forgive me for that. And we have m times root ax square plus bx plus c dx. Okay, so this integral has been reduced into these two integrals. This is obviously easy substitution. If you write this as t, you have dt by root t L times integral, and plus, depending upon what this turns out to be, you can write it as some perfect square. Either we can t square plus minus a square dt dx, actually dx, where t is some lx and not l, naturally have to use l, but you understand what I'm trying to say, is some c, not c also, say dx plus e. Some format of this, you can make a perfect square plus minus a square, or a square plus minus t square, or root of a square plus minus t square, whatever. But you know that all these integrals are known. You know integral of root a square plus minus t square and 1 by root t square plus minus a square. So all these four integrals are known to you. Some is sine inverse and some is but you know all these integrals. I am not remembering that now, but I discussed all of these. So these both are familiar. This is very easy, and this is also known to you. So this method actually works. So remember, seeing this form, use this method approach actually. Okay, so this is one of the ways how to solve algebraic integrals. Okay, so the second is, if you are given, say, this is the same basically, a plus q upon ax square plus bx plus c, then also the same method is useful. So no need to explain this. If you are given this, again do what I told previously. And next is again px plus q root, if the root is above, that is ax square plus bx plus c. If this is given, again try to express this as derivative of this plus constant. So when the constant is taken out, first of all will become easy, and the second constant is taken out, it will either become, this will either become again a square, not a square, say b, some other square, and so I'm not writing it down. But okay, you understand what I'm trying to say. There are not enough variables, I already used 5. So for all these 3 types I told you, the basic general formula that stands is express px plus q as L times 2ax plus b plus another constant m, and then you'll get 2 integrals, both of which will be comparatively very easy if you remember the formula that I told you initially of integrals of root x square plus a square and so on. Okay, so this is how you solve algebraic integrals. And then there is the second part, that is if you have format like this, ax square plus bx plus c upon root px square plus qx plus c integral. Okay, then in that case you write, and dx obviously, dx, then you try to express ax square plus bx plus c as px square plus qx plus c, that is t times this, say t1 times this, plus t2 times derivative of this, that is 2px plus q plus t3 a constant. So here also the approach is pretty much the same, but since it is a degree higher, we try to express it as this, which is the term denominator without the root, plus its derivative t2 times plus another constant. So if you write it like this, on cancelling out, the first term will be root px square plus qx plus not c, say r, p, q, r. Okay, so let's use r. This is not c, this is r, don't confuse it. Okay, plus r and some times, that is t1 times, plus, so this can be easily solved by making perfect square and so on. Second term and third term, as you already know how to solve them. So this approach is pretty standard, trying to write it as a linear combination of the denominator plus derivative of denominator and so on. So if term like this was present, that is ax square plus bx plus c upon, without the root, px square plus qx plus r, then also the approach would have been exactly the same. So with these 5 methods, 5 various expressions, I am trying to tell you what is the general approach that you should take while solving algebraic integrals. So enough of the theory, let's take an example and be more clear on how to do a question exactly. So we have a question right here, that is 3x plus 2 upon 4x square plus 4x plus 5 dx. Okay, so like I told you, try to express 3x plus 2 as L times 8x plus 4 plus t, say L1 and L2. Okay, so we have L1 has to be equal to 3 by 8, so this gives us L1 into 4 plus L2 has to be equal to 2, so L2 2 minus 4 into 3 by 8, that is 3 by 2 left with L2 is 1 by 2. So we have 3 by 8 times 8x plus 4 plus half by 4x square plus 4x plus 5. So like I told you, now you can solve this, easily solvable. So I'm not solving further, but you can see, okay, like a solved example I took, this was very easy actually, but still you get the idea. Okay, so let's take another just to see. Okay, so this one is of another format, 2x minus 4 into root of 4 minus x square plus 3x dx. Okay, so here also I am trying to express 2x minus 4 as L1 times minus 2x plus 3 plus L2. So L1 is equal to minus 1, so minus 3 plus L2 is equal to minus 4, so L2 is also equal to minus 1. So we have 2x minus 4 can be written as 2x minus 3 minus 1 into the other term 4 minus x square plus 3x dx. So this was easy, maybe we shouldn't have used this, only you could see that, but still we are used to a certain method. Okay, so now this is very easy to solve. So these solved examples are pretty easy. In the advanced level I tried to take some question with a more trick or difficulty, as you can say. Okay, so this was as far as algebraic integrals are concerned. So like I told you, after algebraic integrals I have some methods for irrational integrals. So let's discuss that and then we'll move on to trigonometric integrals. Okay, so we have irrational integrals, certain methods I am going to tell you. Irrational integrals. Okay, so let me see. So the general formula that we have here is, okay, so there are 5 methods I am going to tell you. So the first one is easy. If you have ax plus b raised to 1 by n, so all you have to do is n dx. If you have integral of this form, then t raised to n is equal to ax plus b is the substitution that you should use. Okay, so general idea is, if you have function of the form x comma ax plus b raised to 1 by n dx, so it will after transformation become f t raised to n minus b by a comma t n by a t raised to n minus 1 dt. So this becomes this, and which is easy to solve because we have a polynomial in t. The power 1 by n creates a problem, though you can use binomial, but it will go infinite binomial theorem to expand, but with this it becomes easier. So seeing this should strike you as substituting ax plus b as t raised to n. This is the first method. Okay, so the second method we have, if you have of the form x minus k multiplied by ax square plus bx plus c and dx integral. So here x minus k equal to 1 by t is a substitution that works, because using this I will have dx is equal to minus 1 by t square dt, and putting this, I'll, as you can see, if I put x as 1 by t plus k, that is x is equal to 1 plus tk by t here, so I'll get a polynomial quadratic in t, and a 1 by t will come out common here, and I have t here, so this t and this is nothing but 1 by t, and this is 1 by t, so we will have t square, and this is 1 minus 1 by t square, so it is nothing but t square cancels out. So this thing is t, dx is minus 1 by t square dt, and we have something quadratic in t and 1 by t here also. So this entire thing with this cancels out to give us minus 1. So it actually reduces to minus 1 dt upon quadratic in t, which is obviously, you know, by creating perfect square is easy solvable. So the basic idea here is to delete this term and make a quadratic in t. So keep in mind, this is also very useful. First one is quite intuitive, you could have thought yourself also, but the second one, this is important. Many students will not be able to do this if they don't remember what's the proper substitution, so be careful. Okay, so I've told you 2, there are 3 to go. Okay, so the third one is pretty easy, a slight variation of the second one actually. So the third says that if you have 1 upon x minus k actually raised to r root ax square plus bx plus c dx, so actually substitute x minus k equal to 1 by t again. So here you will have x minus k is 1 by t, so you have t raised to r into minus 1 by t square dt by root, this thing will become quadratic in t, and another t will be multiplied here. So seeing that, it will become t raised to r minus 1 minus dt upon quadratic in t. So then you can proceed forward. Okay, depending on if r is 2, then it's good. Maybe if r is greater than that, then you can do something, but it's much easier than this, that I'll say. Okay, then we have, so okay, let's rub this afterwards. Then we have this dx upon root of ax square plus b into cx square plus d. This format, put x is equal to 1 by t, so it will have the same effect. So x equal to 1 by t, so 1 by t square will be here, 1 by t will be here, so and 1 by t square will be here, so this cancels out and t will become, and t will come in the numerator, so it will become very easy to solve. So these substitutions are quite non-trivial, so it's better that you remember them, because in the paper you will not be able to think instantaneously. Okay, so on simplifying this, it will become minus t dt integral upon root a plus b t square dot c plus dt square. Okay, and putting a plus bt square is equal to u square gives us 2tb dt is equal to 2u du. So t dt becomes u du by b, and minus sign is there, and this is nothing but u into c plus d, and t square is nothing but u square minus a by b. So u cancels out, this is minus 1 by b integral du upon bc plus du square minus ad by b. So bb cancels out, so this becomes actually a format du upon 1 by k something u square plus minus l square, so on. Actually this format is generated, so both the cases plus and minus you know how to solve. So basically an integral like this on a simple substitution becomes a very well known integral. So it's just about thinking out of the box, which leads to such various results. Okay, so now we have a last one of the irrational integrals, and then we'll move on to trigonometry after taking some examples. Okay, so here we have the final one is, fifth one says that ax square plus bx plus c integral dx upon dx plus e under root fx square plus gx plus h. If this format is given, all you have to do is try to express ax square plus bx plus c as a1 dx plus e 2fx plus g plus b1 dx plus e plus c1. Okay, so try to express it as this. So if by this you will see that first term will be generated as dx upon root fx square plus gx plus h, which is easy to solve, plus integral cancelling out this upon this, sorry, this is the second term. First term will be 2fx plus g, some constant, that is something, some constant c2, some constant c1 integral dx upon the denominator is same as in the second term gx plus h. This is easy, ln something will be formed, not ln but substitution will create a simpler form. And then finally c3 will be dx upon dx plus e, don't confuse this dx and ds, this is d into x and this is dx, root fx square plus gx plus h. Okay, so this is very easy, very easy. This is also known, and this is what I told you, put x is equal to 1 by t, not x is equal to 1 by t, sorry, put dx plus c is equal to 1 by t. Okay, so this is one of the previous cases that I told you where x minus k was used, but seeing that okay dx plus c is of the form x minus k, so this thing very complicated reduces into three simpler integrals. One of them is not that simple, but still you know how to solve, so it's simple for you. Okay, so these were the 5 main methods, or actually just small tricks that I want to tell you, that what substitution or what should be done in case one of these 5 is given. Okay, so let's take an example to see how to use it. Okay, so here is an example. So first example is this, x, sorry, let's write it again, x dx is here, x minus 3 root of x plus 1. So seeing that this is not one of the general formats, as you can see, so what I'm going to do here is, seeing that okay this root is creating a problem, so a valid substitution would have been or might be this. So let's see, if I use this, so I have dx is equal to 2t dt. Okay, so x is nothing but t square minus 1, dx is nothing but 2t dt upon x minus 3 is nothing but x is t square minus 1, so it becomes t square minus 4, and this is nothing but t. Okay, so seeing that, okay, dt gets cancelled out, we have 2 integral t square minus 1 upon t square minus 4 dt, which is nothing but t square minus 4 plus 3 upon t square minus 4 dt 2 times, which is 1 plus 3 upon t square minus 4 dt 2 times. Okay, so this can be solved easily. So okay, if one of the standard forms that I am talking about is not generated, which may be the case very often, so you use your own brain to see that, okay, let's remove the root and let's try what polynomial or rational expression is formed. Seeing that, okay, tt cancels out, a very easy form is formed, it tells us, okay, this is correct, we are able to solve this. Maybe we could have got stuck, then maybe use by parts, some other substitution. So it's all practice. So seeing that a general form is not formed, it's up to you as how you approach the problem. Okay, so now another question. Given x greater than 1, just for the function to be valid, we have dx upon x minus 1 root x square plus x plus 1. Okay, so given this, so this is the standard format, so that is we have to put x minus 1 as 1 by t, that is dx becomes minus 1 by t square dt. This is nothing but x minus 1 is 1 by t into this is nothing but, so x is 1 plus 1 by t whole square plus 1 plus 1 by t plus 1. Okay, so on simplifying this, first of all I have minus common, dt by 1 by t, obviously 1 by t square is also there, 1 by t square, and this turns out to be 1 plus 1 by t square plus 2 by t plus 2 plus 2 plus, so we have 2 by t plus 2 plus 1 by t, and this thing is in under root, so it turns out to be minus 1 by t integral, sorry, what am I doing, this is 1 by t dt and root into 1 by t, root t square plus 1 plus 2t plus 2t square plus 1, it's nothing but 3t square plus 2t plus 2. Okay, 3t square plus 2t, t square plus 1 plus 2t plus t, so it's 3t plus 1. Okay, okay, 3 3 3, so root this cancelling out, so finally what I get is dt minus sign root 3t square plus 3t plus 1 under root, so making this a perfect square, 3t square plus 1 is t plus half whole square minus 1 by 4 plus 1 under root, so we have 3 t plus half square minus 3 by 4 plus 1 by 4 under root 1 by this thing integral dt. So solve this, okay, taking out root 3 common and so on, this can be easily solved. I'm not doing it any further, just to check the answer. Okay, this is what we get, 3t square plus 3t plus 1. So just be careful in your calculation and remember the final integrals that are formed by heart, so that no time is wasted, that's all. Okay, so these are some examples on irrational. Out of the 5 I took 1, 2, I'll take some more in the advanced level. Now let's move on to another type of section, that is if you have integrals of the form, so it's not generally under the topic irrational, it's just separately I want to discuss. If you have integrals of the form x raised to m and a plus b x raised to capital N raised to capital P. Okay, if you have integrals of this form, so there are 4 cases that I'm going to discuss if this happens, so what you should do and so on, and take an example, a couple, so to show you how it is done. The first case is simple, that is sorry, not P is an not an a natural number. Then obviously the best way to do is open it by binomial theorem. If P is natural number, a plus bx capital N raised to P, expand using binomial. You all know what is binomial theorem, I assume. If you don't, you will learn it, but okay, you should know binomial theorem. So expand it, integrate it. So this is very easy. Everyone could have thought that if you asked in a question. Second is if P epsilon negative integer, positive is obviously natural number, P is a negative integer, then x is equal to small p, this is separate than this, raised to k, where k is LCM of a denominator of m and n. M and n are fractions. If and take the LCM of the denominator and substitute it as this. Okay, so this is one way. The third is, these are somewhat complicated to understand, but with an example you will be clear. M plus 1 by n is an integer, then put a plus bx, this raised to n, as r raised to k, where again k is the same. Okay, where r is a new variable. So try this will help solve. So I'm again saying take examples to make this clear. I'm going to take it just after this. Plus p, these are very complicated conditions, is an integer, then the trick is put a plus bx raised to capital N as r raised to k x raised to n, where again k is the same. So here I have written 4 ways on how to solve this. So basically first one is very easy to understand why it will work, but the next 3 are quite difficult. So example is the best way I can show you why these work and how they reduce the integral to a very easy integral. Okay, so let's take example and see what we have got in our hands. Okay, so this is another trick. So there is a lot of things to learn, several integrals and several methods. So it's a very learning topic, but still if you practice you get perfect. So we have a question here. It says x raised to 1 by 3 2 plus x raised to 1 by 2 raised to 2 dx. So this is of the first type, that is, this is an integer, that is p. So expand it. So we have 4 plus x plus 4 root x raised to 1 by 3 integral dx. So you will get terms like 4x raised to 1 by 3 integral dx plus x raised to 4 by 3 dx integral plus 4x raised to 1 by 3 plus 1 by 2 dx integral. Okay, so solve these 3 integrals and you are done. So this was of the first category. So this should have been easy. Second one is x raised to minus 2 by 3 1 plus x raised to 2 by 3 raised to minus 1 dx. Okay, so this is of the second type, that is p here is epsilon negative integers. Okay, so what we have here is you substitute x as some new variable, say p raised to k, where k is LCM of denominators of m and n, which is 3, because m here is minus 2 by 3 and n here is 2 by 3, so LCM of the denominator is 3. So we substitute x is equal to p cube, which makes us dx is equal to 3p square dp. So substituting it here, we have x raised to minus 2 by 3 is equal to p raised to minus 2 1 plus p square raised to minus 1 into dx is nothing but 3p square dp. So cancelling this, we have 3 upon 1 plus p square dp, which is 3 tan inverse p plus a constant, where p is cube root of x. So as you see why this worked, because taking LCM of this, it makes sure that these all turn into integer powers, and then we are left with a much simpler integral. Okay, So this was another example. So with this example, I have tried to explain you how these tricks that I told you are useful. I'll take a couple more in the advanced section. So now let's move on to trigonometric manipulation, or basically trigonometric integrals. Here also I'm going to tell you about some of the tricks. Okay, so next topic is trigonometric integrals. Okay, this is basically the last topic. So the general, first and foremost, the most important rule is, if you have a function of sin x and cos x dx, okay, so the basic and most interesting thing to do is t is equal to tan x by 2, then dt is equal to 2 dt upon 1 plus t square, actually not this actually. So we have dt is equal to 1 actually sec square x by 2 into half dx. So get 2 dt upon 1 plus t square is equal to dx. So this is what you get dx, and sin x is nothing but 2t upon 1 plus t square, and cos x is 1 minus t square upon 1 plus t square. So all the terms of sin and cos are replaced by these, and dx become this. So you have a whole rational expression in terms of t. So maybe you can use partial fractions there, or algebraic twin identity that I told you, 2 upon 1 plus x4, x square upon 1 plus x4, and so on. Excuse me. Okay. So this is generally what students do when they see sin x and cos x. So maybe there are simpler ways, but this is like a short way to at least simplify the question. So this is first, and I'm going to write you some of the other substitution. There are 3 based on certain conditions. If r of minus sin x comma cos x turns out to be minus r of sin x comma cos x, then the substitution is cos x is equal to t, r of sin x minus cos x turns out to be minus r sin x comma cos x, then substitution is substitute sin x as t. Let's change the pen, wearing out. And if r is r of minus sin x minus cos x is turns out to be plus of r sin x comma cos x, then substitute tan x as t. Okay, so you can try using these substitutions that I am telling you to see how problem gets simplified. Okay, so and then we are left with final 2 or 3 more, and then you are finished with all the methods that I have to tell you on integration. Okay, so let's see. So we have, if your integral is of the form p cos x plus q sin x plus r upon a cos x plus b sin x plus c. Okay, so you see that the method here is similar to that you did in algebraic, that is, try to express p cos x plus q sin x plus r as L times the denominator plus m times derivative of denominator plus a constant plus n. So if you have denominator, then it will cancel out and have some L times integral. Derivative will turn into ln of something, and n times this can be solved by using tan x by 2 that I told you. So all 3 are known, so no problem. And the second case is, if you have integral p cos x plus q sin x upon a cos x plus b sin x dx, then your approach is to express p cos x plus q sin x as L times denominator plus m times derivative of denominator. So now again the same method, denominator will cancel out leaving a constant, and here you will generate an ln term, so on. Okay, so with this I have finished trigonometric integrals with just a little more topic to go, some general integrals of the form sine raised to mx, sine x raised to power m and cos x raised to power n. Let's just write these. So if you have integrals of the form this sine mx cos nx dx, okay, if you have this, so case says that, and obviously m and n are natural numbers, this should be holding. So what we do here is, so obviously if cos is odd, that n is odd, then if n is odd, then sin x is equal to t. If m is odd, cos is equal to t. If n, m both are odd, then either can be used, that is sin x or cos x can be written as t. And if again first even, if n, m both even, then use trigonometric identities to raise them to higher powers in C. So use trigonometry to solve, trigonometry to go to higher powers, okay, higher powers by meaning that, right, you have sine square x, so write it as sine 2x. Higher powers, say we have sine square x, so it can be written as 1 minus cos 2x by 2. That means higher coefficient of x, higher coefficient of x, go to higher coefficient of x, okay. So this is, and the final one is, if this condition satisfies, that is m plus n minus 2 by 2, the pen is running out, okay, m plus n minus 2 by 2, let's just write it again, it's okay, very weird condition, m plus n minus 2 by 2 is negative integer, then tan x or cot x equal to t is a valid substitution, okay. So 1, 2, 3, 4 and 5, these are also 5 points to remember on trigonometric integrals. So with this, after having you told this, I have come to the end of this chapter. So I have told you so many things on how to solve integrals, various algebraic expressions, irrational, x raised to n, a plus bx raised to n, so on, various expressions and various conditions on to when to use this substitution, why to use that substitution, and so on. So from the starting, definition of integration was told to you, then came constant of integration, some general properties, then methods of integration, basic integrals were told, which according to me are very important, so you should learn them by heart, okay, before solving any problem, because they will be used very intensively. And then was integration by substitution, which is also very important, by parts, and then finally was integration by partial fraction, and then some of the general tricks and tips that I told you on certain integrals. So I have come to the end of this chapter. I hope you understood all the points that I was trying to make in the chapter. If still you have missed me at some point, rewind back, see the solved example, which is very important. Sometimes the theory is not clear because I have written conditions like this, so you won't remember this, but I will try to take some problems on this, or if you can yourself take problems if I haven't taken enough, if you don't understand from these solved examples. So take problems. Integration is all about practice. So I would like to thank you for listening to my lecture. I hope you enjoyed it. That's it for me. Thank you.